Hey everyone, I just want to talk briefly about functions of more than two variables. And so in general, these higher, in general, we might consider a function of n variables. And so we say a function of n variables is a rule that assigns a real value to an n tuple. That is, we can write that real value as z, and z is written as a function of this n tuple, where all an n tuple is like an ordered pair. But instead of having two of them, we have n of them. And so now we think of the input as our function as this distinct set of these different n values of x, plugging all these n different values of x into our function and using the formula that is provided will give us the single output value, which is the output of our function, which we might label as z. And so when we're working with these functions of more than two variables, we might not always label those variables as x1, x2, x3 up to xn. Depending on how many there are, it might make more sense, or if there's a given context, it might make more sense to use a different labeling system, but the idea is still the same. So if we have a function of three variables, we could write that function as z is equal to f of x1, comma x2, comma x3, or it might make more sense to write that function as f of x, y, z, and then we can't use z as the output as well as one of the inputs, so maybe we'll call the output w. And this makes a lot of sense if we're thinking of something like a temperature function, where we're thinking about what is the temperature of a point in space. Well, for that point in space, it's going to have x, y, and z coordinates, and that temperature at that point will be like our w value. It's really when we get to four or more variables that we stop using like x, y, and z. So if we have four or more variables, we might write t is a function of x1, x2, x3, and x4. Although even in this case, we still might have some context where it makes sense to use some of our old labeling system. For example, if capital T was to determine temperature at some point in space, maybe the first coordinate is the x coordinate, the second and third are the y and z coordinates, just really describing that physical location of that point in space. But temperature changes as time changes, so maybe it makes sense to label that fourth variable or one of our earlier variables as lowercase t, where that represents time. So there really are lots of useful applications and important applications for these functions of higher variables. We just have certain limitations when we're trying to work with these functions of more than two variables. Another very common example of a function with a lot more than two or three variables is something like a revenue function for a very large company. Maybe the inputs for that revenue function are the number of the different types of products the companies sell. Then they'll have to use that information along with the price generated by selling each of those items to create the total revenue function. Another thing that we'll eventually kind of see is instead of thinking of the inputs for one of these higher variable functions as an n tuple, it might make sense to think of it as an n-dimensional vector instead. But the real point of this discussion is to talk about the kind of this notation for these higher dimensional or higher variable using functions. And what we also want to get through this example is that it's not always easy to visualize these higher dimensional functions. In fact, sometimes it's impossible to do so. For example, if we had a function like w is equal to x squared plus y squared plus z squared, well then a point satisfying this equation is going to be x comma y comma z comma w. And so, well, that point would have four coordinates to it, and that would require a four-dimensional space to graph. Well, we're limited to three-dimensional space when it comes to graphing, so there's no way to graph the actual function that we have written down here. The best that we can do is similar to what we did for our three-dimensional surfaces and look at traces or intersections with the lower dimensional space. What I mean by that is that we cannot graph this function, but what we can graph are like level curves, or really more appropriately, level surfaces for this function, right? If we set w equal to 1, then our equation would become 1 is equal to x squared plus y squared plus z squared, and we know what the shape of that surface is going to look like. It's going to look like our sphere of radius 1 centered at the origin. Well, we could go ahead and set w equal to 4 or some other constant values. It wouldn't make sense to make it negative here because everything else is positive. But if we set w equal to 4, then we wouldn't have a level curve. We'd have another level surface, and that would look like 4 is equal to x squared plus y squared plus z squared. But that would give us a sphere of radius 2 centered at the origin. So again, we cannot visualize and graph this four-dimensional function, but what we can look at are projections of our four-dimensional object or shape into our three-dimensional space using the same process we used to take a three-dimensional surface and project it onto two-dimensional space using level curves or traces. Unfortunately, however, the buck really kind of stops there, and we can't do this for higher dimensional functions and spaces, right? If we have a function of more than 3 variables, like a function of x1, x2, x3, and x4, maybe call that like t, then a point that would be on this surface or object would have coordinates of x1, x2, x3, x4, and t. And well, that is like a 5-dimensional coordinate. And so the actual object would exist in 5-dimensional space. And if we were to try to look at a level curve or a trace, it would take up 4-dimensional space, and we can't visualize that. And so we still want to do this similar analysis with these functions of more variables or these higher dimensional functions. However, we cannot really do so visually. And so that's why it's really important to have an algebraic approach to all this material as well. And what we eventually kind of do is figure out an algebraic approach for these lower dimensional situations that we can visualize, and then extend those ideas and figure out how they could possibly work in the higher dimensions or spaces that we cannot visualize.